everyone. Welcome to the Future of Proof Systems panel. I'll be the moderator today, and thanks to Zurich Spark and Privacy and Scaling Explorations for putting this together. The sort of most exciting forefront for programmable cryptography over the last 8 years, I guess, has been ZK snarks. And in particular, a lot of that has been enabled by performance improvements over the past 8 years, starting from GROT 16 all the way now to things like Lasso and all of these new exciting lookup protocols and SumCheck and all of these cool things. So I'm very lucky to be hosting this panel with the sort of group that is quite a bit responsible for the 80 years of innovation. I've personally learned a ton from almost everyone in this group over my career, so I hope we can figure out a way to extract some of that for everyone joining us today. Yeah, so on that note, let's just start with some introductions. Mary, do you want to start us off by sharing a bit about yourself?
Hi, I'm Mary Malla. I am a cryptography researcher. I do lots of work on zero knowledge, especially on the theoretical side, how to make them fast, how to actually check whether they're secure or not, which is a big part of it. I also I work for the Ethereum Foundation and also PQ Shield, and yeah, I'm happy to be here. Thank you.
Awesome. Thanks. Yeah, do you want to go next?
Hi everyone, my name is Ye, the co-founder of Scroll. Scroll is a general purpose scaling solution for Ethereum. So basically you can imagine it's like faster, higher throughput, cheaper than Ethereum, achieved by this kind of amazing ZK technology. We built a bytecode level compatible ZK EVM with the PSE team as well as several community members to make this happen. And personally, I have been working on ZK research for the past 5 or 6 years, also making prover faster, more from the hardware acceleration, like how you can use GPU, AC, FPGA to make prover faster, and also some theoretical research around like how you kind of what's the mathematical behind this proving system, but now focusing on like how we can use ZK proof system in practice to build some applications like ZK EVM.
Hi, I'm Liam Egan. I'm a cryptography researcher. I work at a small company with Ariel Gabazon. We do like collaborative research, mostly into lookups and folding lately. Yeah, just working on trying to make provers faster.
Hi, I'm Ing Tong. I used to work on the Zcash project and was one of the authors of the Halo 2 proof system. Right now, I'm at Geometry Research, and we collaborate with projects who use ZK snarks and other kinds of programmable cryptography. And recently, I'm also interested in programmable privacy beyond ZK snarks.
Amazing. Yeah, thank you all for the introduction. It's great to have you all here. I think one of the reasons ZK as a space has like developed so much faster than any academic space is partly because of the tight feedback loops that exist. So it's great to have this panel here where we have like people cutting across the stack. So for example, Ye is building a ZK EVM. Ying Tong is one of the authors of the library Ye is using. And Liam and Mary have been doing a lot of work on lookups and a lot of the underlying research. Awesome. Thank you. So yeah, as I think I have already alluded to quite a bit, I think one of the topics that has been really hot lately is lookups. So maybe let's start this panel off with some discussion of lookups. So with lookups, I wanted to take sort of a deeper dive on what the performance trajectory of lookups in ZK snarks has been and how they have improved ZK snarks over time. So historically, the idea of lookups has come about with this paper called ARIA that Mary was involved with. So I'm curious, Mary, do you want to share an introduction to lookups and how you thought about it at the time?
So lookup arguments are something which have existed long before zero-knowledge proofs existed. They're used in computer architecture systems more generally. And the idea is that if you have a computation that you're having to do over and over and over and over again, then rather than actually compute it over and over and over and over again, what you would do is you would store it. You would store it in some big table, and then in order to compute it the next time, you wouldn't compute it, you would do a memory access in order to look it up and see what the answer is. So when it came to, is there a way to do these things faster? Is there a way to take the lessons that has been learned from computer architecture and maybe import it to zero-knowledge proofs? Actually, the person who I first heard having this idea was one of my collaborators called Suno Jacobson. And he sort of said, what about these lookups? These could work. And at this point, we were very much on the theoretical side of this. ARIA was never implemented, and we didn't really want to implement it either because we knew that there were huge improvements that needed to be made before that was worth it, which have since happened now. But even on the theoretical level, we could sort of see our numbers going from being quite high to quite reasonable, so that was quite fun.
Yeah, amazing. Yeah, as Marie said, I believe this was one of the first research paper descriptions of using lookups in ZK, but I believe it wasn't until like a couple of years or maybe more until plookup for Plonk came out, as well as Halo 2 lookup. So Yingtong, I would be curious if you want to share sort of the leap between ARIA and what Halo 2 lookup.
Yeah, so as you mentioned, Halo 2 lookup is a simplification of plookup, but both of these are pretty similar in that they just reduce the lookup relation to a polynomial identity that you can check in the normal IOP. And yeah, basically the trick is to express this lookup relation in the form of some constraints that you can apply locally. And with the help of some verifier randomness, you can check this globally. So yeah, Halo 2 lookups, and the Halo 2 library in general is very flexible. And a lot of my work in the past few months has been to experiment with replacing the Halo 2 lookup with some of the newer log derivative-based lookups that have come out.
Exciting. Yeah, so that's very exciting. I know, so one of the log derivative lookups is CQ, which has been co-authored by Liam. So Liam, I would be curious if you could share a little bit more about the gap between Halo 2 lookup and MV lookup, CQ, and sort of the family of log derivative lookups.
So there's sort of a algebraic transformation where you can take products to sums. You might be familiar with like the analytic logarithm, like from calculus or something, but you can do the same sort of operation over a field because the log derivative can be written entirely algebraically. I mean, in a sense, a lot of the lookup protocols, like lookup, for example, take advantage of the kind of commutativity of multiplication, and so if you can move to addition, that can be cheaper, and so MV lookup, CQ, all kind of like, I don't know, use the same fundamental trick. CQ is part of a family of kind of other lookups that was proceeding sort of in parallel, or I guess in parallel, starting with like calc, which Mary was an author on. These allow you to do lookups into very large tables. So like lookup or other lookups, you sort of construct the values you're looking up in the table in circuit. And what calc allowed you to do was pre-compute a bunch of stuff so you don't have to bear the cost of the entire table in circuit. And so this was sort of improved in a series of works, I guess culminating in CQ.
Amazing. Yeah, it's quite interesting to see how sort of from ARIA there was this idea of lookups, and then it really shined in implementation or tooling when it was put into this like modular proof system of Plonk. And then from that, I suppose it has now led up all the way to CQ and beyond. I would be curious to hear from you how you view this from like an application perspective, lookups and how you use them in ZKVM, for instance.
Sure. So from application side, so just to add more context to what, so previously it's more like going through the literature of lookup tables to the implementation to differences. So from application, so we only need like, if you are building a ZK circuit, what you really need is like, okay, so there are two types of lookups. One is a fixed lookup table. So for example, you want to prove that some variable is within some range between like 1 to 15, for example. And then you can kind of have a table storing all those kind of values. And then like in your circuit, every time you need to check the range, you just need to look into the lookup tables. And that can, that can save a lot of like the circuit costs, especially for some ZK unfriendly opcodes or some operations, for example, range proof, for example, bitwise operations, those are very expensive, and you can prove that very cheaply using this lookup because you don't need to kind of decompose every variable into bits and then look up into this kind of complex, like fixed, because you have this fixed lookup. And the other kind of very, very kind of interesting use case, which actually enabled ZK EVM and ZK VM is that there is something called dynamic lookup, which means like you are running a program and then you kind of, in your previous instruction, you want to like, write some kind of variables into a lookup. So that lookup is generated on the fly when you are computing this program. And then later when you are like reading, like, so in other lines of your program, you want to read this variable, like you look up into that lookup tables, you generate it on the fly, and then like, you can prove the consistency between. And it used to be like before lookup table, people used to use a Merkle tree because you can store your elements in a Merkle tree, and then you only need this kind of Merkle tree root as digest, and then every time you need to prove a path to prove that this element exists in this tree. But now with lookup table, you only need to kind of generate this lookup on the fly and then prove like this kind of polynomial equation to very efficiently prove like multi-elements belong to this storage, and that's very, very efficient. And also like this lookup has been like it used to be like the circular simulation used to be R1CS, Plonkish, and then lookup is very similar to actually modern like CPU architecture where you also have this kind of memory, and then like you can look up to save some kind of cost. So that's, and even CQ is like part of the idea from cache where you can kind of have something stored there and reuse that. So I think that's very, I think those are two largest use cases for application. Either like, it can use this fixed lookup to solve some ZK unfriendly opcode optimization, or it can be dynamic lookup table where you are running some VM-like program to kind of prove that very efficiently.
Yeah, definitely. So you've already talked about the distinction between fixed lookups and dynamic lookups. So one of the things that I early on, when I was reading about lookups, I saw was this idea of fixed lookups taken sort of to the extreme by Barry, who's actually in the audience, in this post called Lookup Singularity. I'd be curious what I guess lookup singularity means to, I guess, any of you. This is, I guess, an open question.
I mean, to me, having read the paper, it says that what they mean is that you have just one lookup and that's all you need in order to cover, in their case, they're talking about the RISC-V architecture. So this is not quite true. They have one lookup for almost everything, and then there's just one operation which they can't quite cover. But the general idea actually is to try and make things simpler for developers, like even more so than we want things efficient, which we do. One of the big motivators here is if a developer, rather than having to say, in order to prove that this is in range, decompose stuff and then check bit by bit, instead I'm just going to do one lookup, this is like simpler reasoning, so it just leads to less errors.
Right. Yeah, it's definitely very interesting to see that there is motivation of developer tooling already sort of trickling down to the research level and turning into papers. But yeah, I would be curious also to hear from Jingtong. How do you think tooling for lookups should look like?
Yeah, it's a good question because when we were looking at implementing CQ, like CQ comes with ON squared preprocessing, and it becomes, when your n equals like 2 to the 30, this becomes like a hardware consideration. So yeah, how long would you need to run this setup? So I've heard like on the scale of 6 months. And like where would you store it? How would you make it accessible to provers that are less powerful? So yeah, when you're actually trying to build like a usable implementation of it, you need to start considering all these, basically like, but O(n) squared becomes very real. Um, yeah, so yeah, I think lookup singularity sounds nice, and we also need to make it accessible to weaker provers. Yeah.
Right. Yeah, I would be curious to hear from Liam as well. Yeah, how do you think about, I guess, CQ, which does have a n-squared pre-processing step, versus, for example, Lasso, which I guess does not have such a step, but has the decomposability condition baked in?
Right. CQ has n log n pre-processing. It's like kind of running an FFT. But yeah, no, this distinction between decomposable and arbitrary tables is really important and interesting, and that's a big part of Lasso. So the idea is that if you have a table that's very structured, like say the integers or XOR or something like this, you can avoid the pre-processing step. And I mean, intuitively, it kind of makes sense, right? There's a lot of structure there. It should be possible to describe it more efficiently, but that's what they go through in the paper. Yeah, it's an interesting question. Like so I don't know. There's like different types of considerations. So one thing is like with Lasso, if you have small values in your table, which you would for the integers or for XOR or for something like that, you have this really nice property where you don't have to commit to any large values. Whereas in CQ and like log derivative based lookups, lookup, etc., you do have to commit to large values. So this is another sort of point in favor of the Lasso style. I think it's worth pointing out also that Lasso, at least as I've understood it from conversations with people, is sort of like a general framework for doing a little bit like what people have been doing. So for example, with a range check, right, like what you would do is you'd split it into pieces and you'd look up each sort of digit, right, in a big or smaller table. Lasso is a way of kind of like formalizing that and presenting a simpler interface to the point of programmer tooling. Yeah, and so in Lasso they use GKR, and so that like, it's a protocol built around like another lookup protocol, and you can use other lookup protocols inside of it, like log derivative, for example, which might have benefits when recursing, so you don't have to prove log squared hashes in the recursive circuit. And I mean, I feel like I'm kind of rambling here, but yeah, and then the other tables, like if you have a Pedersen hash or something and the values are big, you know, what is the trade-off there? Because you don't get the benefit of never committing to big values if the values are already large.
Yeah, it's definitely quite interesting. As you mentioned, it's like people have already been doing sort of the trick that Lasso is based on in the application level, and now sort of with Lasso they've taken it down to the like proving system level and already see benefits of like doing so. Yeah, I'm curious to hear from you, Ye. What do you think about the decomposability structures and how I guess the KVM and all these circuits are using it today?
Yeah, I think with kind of this, because one thing like one important bottleneck in the KVM is that we use too many lookup tables, and like lookup table we used to like use initially implement by like the Hello 2.0 lookup table, which will introduce some additional commitment and also need some sorting for kind of all those kind of column elements, and then like that's. Later, like we move to this kind of like Intune, what Intune is working on, this new MV lookup table implementation to kind of reduce the lookup table overhead. So what I see from this kind of literature of lookup table is that so imagine that you really have some large lookup tables. So because imagine like EVM word is 256 bits. And what we used to do is that because even if you have fixed lookup table, you can't have a 2 powers 256 size, like, you know, brute force for all the kind of, for the range check you need. But if you really have something like that can efficiently handle like, you know, 2 powers like 60, 2 power 100 size lookup tables, and the whole logic can be overly simplified. You don't need any kind of, so I think my understanding for this lookup singularity is that eventually for all the computation you can have a table just storing all the brute force results. And the reason why we can't do that right now is that because imagine like you are computing a hash function, because hash function, like you can have arbitrary input and then you can have some kind of arbitrary output. You can't store all the possible input and output pair. So that's why you have to prove that on the fly. But if you can really prove like unlimited size of lookup tables, you can even like do hash just through like one lookup into some tables which store all the possible pairs. So I think that will unlock a lot of applications. For example, like I think in CatCheck, in SHA-256, where there are some very efficient constructions based on lookup tables. And if you can imagine, you can like use larger lookup table, I think there will be a bunch of applications which can be unlocked by this. And also like for ZK-VM specifically, I think we expect to see, because most of those literature rely on like even Quark, CQ rely on some, like it's still for fixed lookup table. And we see like MV lookup table and lookup, all those kind of new lookup tables has the potential to kind of do this for dynamic tables, and which will be very, very useful for ZK-VM. And also, because as I mentioned, like, it's not just the storage part, but also like when in ZK-VM, you have separate circuits handling different like CatCheck, pairing, all those different circuits, and the composability is very important to look up between like, like for example, I can outsource this CatCheck into a specialized circuit and look up back. So I think that's also like composability is also very important in like for this having these dynamic lookup tables.
Yeah, definitely. I think there is this element of like, because the operations need to have some amount of structure for the protocol to really benefit. One open question that I know some of us have thought about before is wondering about what operations are not well structurable, things of that sort. So I'm curious if any of you have thoughts on like things that are unstructured and are not optimized by Lasso at the moment.
I think from our understanding, so initially I think there are like two good motivations behind Lasso. One is that because you have these really, really large lookup tables, and then you can simplify your logic of virtual machine, because all the kind of, you don't even need to, the end goal will be you don't need to write any line of circuit, you don't need to write any gate, you just look up. Everything is like your programming language for circuit is just look up into some tables. And then it's very easy. So firstly, like from Lasso, like in theory, it can be efficiently proved. So that's why you can improve the prover efficiency. Second thing is on the security side, where because you only have this kind of lookup logic, so you can easier to be formally verified, like your virtual machine had no bug, because it's the logic is too simple because it just look up something. But I think from our perspective, the consideration is still on the performance side, like whether Lasso is really, really performance enough, like to kind of solve this problem. From our kind of benchmark, it's still like, we don't know whether like go through this, like only use lookup and the efficiency of Lasso can really solve the problems we are facing. And even like Lasso has this kind of smaller like field for this like multi-scalar multiplication on the curve, but it's still less efficient than like Fry in some sense. So that's why like we are still looking into how performant that is in practice, not in theory, because you really need to combine the best practice of both sides.
Yeah, certainly. Yeah, it's definitely very interesting problem of like fitting your operations into structure, as well as from the other side, improving the proving system so it can support more structure. Certainly. Yeah, so I think so through this arc of lookups, starting with ARIA in 2018, it seems like over just the last year or so, there have been a number of sort of major milestones that have been accomplished. So starting with CQ and some of the Quark line of work, we got to prover time being independent of the table size, but with the asterisks of pre-processing. And then it seems with Lasso, or at least with Lasso for structured tables, we have the lookup singularity, which is the ability to do lookups for sort of arbitrary sized inputs. Yeah, so from a more, I guess, general perspective, it seems like there has been this agenda for lookups that was somewhat clear, or somewhat, I guess, not clear that it could be accomplished, but clear of what was wanted in terms of performance. I would be curious if there are open questions like this that Mary or Liam, you guys think of when you think of, I guess, the future of lookups.
Future of lookups specifically. I mean, I would say there is definitely a question of we now have that we can have fairly small tables with the lasso thing in which we can prove very, very big statements. And whether we can do this in more expressive ways such that it is actually useful, it can actually be applied in the systems, is clearly something where there would still be some work to do. But probably, I mean, when lookups sort of became big, it was because it was an underexplored area where people didn't really use these things in our systems yet. So we were able to make massive improvements very, very quickly. I would say if we want to make the same kind of improvements again, certainly in terms of proof of speed or anything else, then I would say we need new ideas at the table.
Yeah, Liam, anything to add to that?
Yeah, I think that's right. We need more like new stuff. I'm not sure how much can be squeezed out of lookups. I mean, there's like some peripheral questions, like can you do CQ for some tables without running the setup if it's structured enough in a particular way? And I think, probably, but I'm not sure if it's competitive with Lasso. But yeah, like to get the real kind of dramatic performance improvements, we'll need more like, sumcheck, GKR kind of developments.
Yeah,
I
so
actually have a question about like the next iteration for lookups, which is, would it be interesting to make these lookups zero knowledge? Because a lot of these newer lookup schemes that come out, they, at least in their papers, they didn't say here's a zero knowledge version. Yeah, and I wonder, is the lookup singularity, can it still be zero knowledge?
There's a follow-up to CQ, I mean, just for example, that makes it zero knowledge, came out recently. Yeah.
I might have something of an answer to that. So with a lot of these proving systems, what people are doing at the moment is they have a very, very large proof that they're trying to demonstrate is true. And what they do is they typically put it inside a recursive structure where you have a proof of a proof of a proof of a proof of a proof, which kind of means that if you want zero knowledge, then it's only the very final layer that needs to be zero knowledge before you get zero knowledge for the full system, which is kind of how people are justifying with these lookup arguments of, oh, don't worry about zero knowledge, it'll be fine. And I think for the applications that we're seeing today and for the things that people are wanting to use this for today, that's kind of true. But you can imagine a situation which we might see more and more of in the future where zero-knowledge proofs aren't made by a single party, but in a more distributed setting where there's lots of parties who are communicating together in order to prove a statement, especially if you're talking like TPC, MPC type applications. And for that, we would probably see zero-knowledge becoming much more important.
Yeah. The other part that Liam and Mary, your answers alluded to is that we need other ideas besides lookup. So I am curious if you have predictions on what would be the other ideas.
I mean, obviously, if I had a clear idea of how can we make zero-knowledge proofs 1,000 times faster, I would publish that. But in general, I would expect it to come from more advanced areas, like this was the case with lookups. It wasn't the fact that we came up with them originally. It was the fact that we looked at other fields, other areas, and we're there like, okay, what can we extrapolate? What techniques that you've developed in very sort of serious ways can we export into the zero-knowledge world? So this is where I would look.
Yeah, that's a great answer. I know also, you might have some thoughts about the use of sumcheck, for example, for future improvements. I'm curious if you want to share something.
Yeah, I think like we do have some ongoing like open research direction around like how you can use GKR to kind of prove a lot of stuff very efficiently and prove especially virtual machine where you have this repeated structure, because there are many like kind of like good advantages of GKR. For example, like one thing is that because you only need to commit a small number of witnesses. For example, like in all the kind of Halo 2 plunkish all the proof systems, including like you use lookup table, you still need to commit all the witnesses, all the lookup elements, and then like so this commitment, because you need to commit such a large table, so it's very expensive. And so with GKR, like because it's a layered circuit, it's very definitely hard to write because it's different from this kind of normal like thematics you are normally using in writing circuits. But one good thing is that you only need to commit to the input layer, which significantly reduces the overhead for commitment. And also because it's orthogonal to the smaller field, and also like we see like a lot of folding scheme coming out like months ago, and actually there are some, if you look really deep into the paper, the magic is related to like GKR and sum check, and either like you fold at this stage or later stage. So we believe that, and also we see some really great benchmark from different teams around like why it can be extremely fast. So that's why we are exploring this direction, and also even within lookups like this field, I think there is lookup, which is a GKR based MA lookup, I think, which we think can be like, if you only build one GKR library and you can support both lookup tables and the general computation for layered circuits, so that will be very efficient. But that's still very, very open, and we are still doing a lot of like benchmarks, so haven't committed to this, but it's something which I think a lot of like ZK community are interested in working on together, like lookups and a general like, how you improve your proof system performance using GKR.
Liam or Yingtong, anything to add to that?
I think GKR is interesting avenue to explore. Maybe underexplored, or at least in some circles. I mean, obviously people have been working on it, but yeah, avoiding committing to things is great. Committing to things is expensive. I don't know. It feels like we are reaching or have reached a point where to get the best sort of performance is really empirical. It's not like the kind of thing you can just think about and come up with something that's obviously, I don't know, better. Maybe not. Maybe somebody will think of something. But yeah, like different trade-offs, right? Amdahl's law, if your proof has 3 components and you make one of them 0, it's only 30% better. So it's like you have to experiment and see like what the trade-offs are in terms of improving things.
Yeah, and another sort of speed up is going to come from hardware. It's already coming from hardware. And I think, yeah, these sort of expensive computations like FFTs or MSMs, if we design fast enough hardware for them, can be like less of a burden. But yeah, hardware always comes with its own considerations, like input output is a bottleneck. So yeah, but yeah, that's another vector for optimization.
Yeah, so maybe let's switch gears a little bit. I know you already talked a little bit about how it's difficult to program GKR versus sort of our currently existing models. And then we also talked a little bit about Halo 2. So actually, I would be curious to hear from you, Yingtong, about Halo 2. How would you describe Halo 2 as it exists in its form right now?
Yeah, so Halo 2 is still a pretty low-level programming language for writing ZK circuits. But I think what's special about Halo 2 is that it's very modular. And so, yeah, the defining feature of Halo 2 is probably the arithmetization level, where we transform a program into constraints. And then below that, we have like polynomial commitment scheme, which actually the popular forks of Halo 2 have swapped out. And they're using KZG instead of the original inner product argument. So I think, yeah, a lot of the tooling that has grown around Halo 2 is at the first layer of arithmetizations. So I've seen people do like formal specification of Halo 2. Recently, Axiom made this like Halo 2 REPL, which is a web interface to write Halo 2 circuits using JavaScript. And yeah, so I think the Halo 2 ecosystem is really, really diverse because Halo 2 is so modular. Yeah.
Right. Yeah, when I was first introduced to Halo 2 by Yingtong, besides having a really steep learning curve for the arithmetization itself, one of its defining features seemed to be how many forks it had. I'm curious to hear your perspective, Ye, on the sort of open source.
I think one thing which is very unique to Halo 2, I think it's because I think like 2 or 3 years ago when we start, Halo 2 is the only fully open source library that has this kind of great optimization, support plunkish, where you can represent your circuit using lookup table, using kind of custom gate, and support all those kind of like custom way to write circuits. To me, like Halo 2, the first impression for Halo 2 is like it's like a Sudoku for like you basically have a like table. You put in some numbers, and then you define some rules, like whether this cell equal to this cell. And this is actually exactly how I explained to some of my friends doing theoretical computer science. So they want to try writing circuits. I told them like you basically need a like paper, and then like have a table and write some numbers and define some rules and then like which is equivalent to this program logic. And then like I think after that, like because it's initially developed by Zcash, there are so many branches, like for example, like there is Halo 2 CE. CE is short for Community Edition, which will be used by a larger, we expect to use by a larger community with more feature requests. And then like there is Halo 2 KZG, which replaces the commitment part with KZG. And then like I think Axiom and some other teams also building some other branches like Halo 2 Leap. It's a framework for you to write circuit easier. So I think one thing, so initially everyone had good intention to kind of contribute back to Zcash upstream, because that's where the fundamentals of the code that come from. So we definitely want to kind of push all our performance optimizations into this repo. But the actual problem is that because the projects are very, very different. Like for example, Zcash is very, very security driven, and it doesn't need a lot of features. Like for example, we add this kind of like challenge API to kind of generate some randomness in circuit. But maybe they don't want this kind of to be compatible with this part. And also a lot of optimization might be aggressive, so they want to take a like slower step to accept. So that's why there are there are different branches, and also there are different requirements. For example, like because we need to verify proof on chain, which means we need to have a very small EVM friendly verifier. But for them, like it's fine to have this kind of like based on this recursive like iterate curve, so that because they only need to verify in Rust program. And so it's basically all the needs drive to different these branches. So I do feel like in the future, when we start like maybe this community effort, we can start with some kind of better spec of how I think Halo 2 is already super, super modular, but how to make that even more modular and even more generalized for everyone to use. Because I definitely heard some complaints because people are trying to reuse the circuits across different forks. But sometimes there's catch-up implement here, sometimes catch-up implement here. You can't really port that circuit directly to this. So I do feel like there need to be some more work when you designing a circuit to be more modularized, and because you can share, because it used to be like every project builds their ZK library, and then it's really bad because Halo 2 is a good example for why having a community is super, super important. So I think definitely having that join a community and developing this way is a good way to go, but you need to be really careful around high level spec and something like that. Another thing just add to this is that modular sometimes also doesn't work because we are looking into why Fry can be efficient, whether we can just change the polynomial commitment from KZG to Fry can make everything become 10 times faster, for example. But the reality is not, because Fry also to make Fry and those kind of smaller field polynomial commitment game really fast, you also need some kind of batching and a lot of techniques related to how you handle the commitment scheme, improver. But in KZG, in this kind of modularized framework, it's just committing every column. It's a different workflow. You need to tweak a lot of things, so which makes things a bit harder. So that's why there's a struggle between the best engineered one zero-knowledge proof system, or it's so modular, and then everyone want to kind of add module to this. So it's a balance, depends on our application needs.
Yeah, I think this is sort of an instance of zooming out. It's sort of the industry and research is moving so fast that there is all this trade-off space that has opened up, and people are exploring it, but with tools that are sort of not fully ready. Yeah, there's definitely been a huge explosion of Halo 2 4x Plonky and like all of those family of Fry-based proving systems. And yeah, that actually leads me to something sort of also more zoomed out. I know, Mary, you recently gave a talk at a NIST workshop about standards. I'm curious how you see this situation and how you think about ZK-SNARK standards.
I mean, I would say that there is a general phrase that I'm sure everyone in this room has heard before, where people say, don't roll your own crypto. And I'm there as a cryptographer going, so about this rolling my own crypto business. I think that there is very much a lot of pressure in our industry to move things very, very fast, to develop papers as soon as they come out, to look into doing things without even documenting them at all sometimes, to maybe have a protocol which works and is really good, but there's no documentation of it. And the standards movement is trying to fight against that, basically. It's trying to say, yes, it's great that there's research. It's amazing that research is happening, that development is happening, that we're building these protocols, that we're making applications possible. But it would also be good if, alongside that, there could be an effort which is maybe a bit more conservative, which moves a bit slower, which isn't necessarily implementing the state of the art, but for which you can be fairly sure that anything that comes out of that effort has genuinely had lots of people looking at it, lots of people scrutinizing it, lots of effort going, not into just writing the first research paper, but then into writing a specification for that paper, reviewing the specifications, having lots of different people looking at it, and generally just being slower and more cautious. And I think this is what is really, really needed to move zero knowledge, I would say. It's already a little bit mainstream, certainly in the blockchain ecosystem, but move it much more mainstream in general society.
Right. Yeah, I would also be curious to, I guess for anyone, which layer of this sort of stack do you think is like the right one to start standardizing? So I guess for context, before we had R1CS, which was sort of the gold standard that you could just port across circuits into like Circom. You had ArcWorks and a lot of other library ecosystems. So that is one layer of arithmetization where you can start with standardization. And then there's deeper layers, as sort of Ye and Yingtang were alluding to, for example, building modular proving systems themselves and having standards for those.
Yeah, we definitely want some standard. But it's so hard to have a standard because even like you look at just one component, which is the polynomial commitment part. So it's very easy to define, like you want to commit to a polynomial, here's a like proof, here's the opening. But the problem to define this kind of having this standard is like, because after you have this, like one important thing like, is about the performance. So even if you have so many different polynomial commitment scheme, you can't even like have a standardized benchmark for how you compare across different polynomial commitment scheme, because some are like smaller field, because you have smaller field, so it influences the way you express your circuit. So it influences like, how many polynomial commitment scheme you need to use to commit to the same computation. And also because some, like for example, like large field, maybe it's not efficient, but it can be like accelerated by ASIC or GPU really fast, or there are some folding scheme to efficiently aggregate, or like, doing something like fancy to make that faster when you have a large, when you're handling different application, like, for example, some data parallel application, maybe you can batch, so it's very, very hard to, because it really differs per application. And I think having some general standard about like, maybe soundness around like, for Stark, because one big concern is that people only look at the performance and don't really care about the security behind. So maybe having some standard about security is definitely very important to the whole industry. But I think for the concrete, like, framework, you can define, this is a field module, this is a polynomial commitment like module, this is IOP level, this is a R1CS or like, Planck level. Like having that standard is great, but in practice, I don't know like how many, especially we see the trend, like, we don't know how many people really kind of want to adopt this different standard, because even for R1CS and Planckish, like R1CS is still very efficient for some kind of, like, if you have a lot of linear operations, R1CS can still like improve a lot on that front. So I think we expect to have something, but I think firstly want to have some fair comparison around like, what's a performance prover, what does that even mean, and how many benchmarks you want to have. For example, there are catch check, there is like, ECDSA, there is maybe some normal operations, and then having that as your like basic standard for performance, and then like at least when you compare, like, okay, so this proof system is performing on this one, on that one. This standard will be used for most application developers, and then like security, and then like if you really want to go deeper, I hope to have modularity, but I think it's very hard.
Yeah, I like when trying to implement CQ in Halo 2, we realized that we could not keep the abstraction over the commitment scheme because yeah, CQ equals like KZG. You cannot use another commitment scheme. Whereas yeah, prior to that, your Halo 2 fork had tried to abstract over IPA and KZG, right? And yeah, I agree with you. Like, I don't think the purpose of a standard is to like make it the most performant for everybody. But as you said, like to suggest like guidelines for a secure implementation, and actually to like be general enough to be useful for most of the existing projects. Yeah, I think working with Mary on this standards effort, I've realized that, yeah, there's a tension between making it too general and therefore like sort of losing the descriptiveness of the spec versus like, yeah, making it too specific and running the risk of becoming obsolete before the spec is even done. So yeah, I think we need to keep in mind that the point of standards is mainly for security, and it's for yeah, like it's for a reference, and it's not for optimization. Yeah.
Yeah, I love that standardization through fair and clear benchmarks for actual applications. As we're getting close to the end, I think this is probably the most fun part, or the part I was most excited about. I have some miscellaneous items that we can walk through, and I would be curious to hear what people's predictions and thoughts on them are. So maybe first, Liam, I will ask you about FFTs versus SumCheck. What do you think is going to happen in the next 3 years with that?
Well, FFTs have n-log-n computation. SumCheck has linear computation and log rounds. Some people say that FFTs are more parallelizable, and that's better. And other people point to the asymptotic benefit of SumCheck. I don't know. I don't know what's going to happen. I think there is like a space in between, like some checks with different sized rounds. So people do some checks with folding factor 2, which is sort of the standard way you do some check. But you could do it with any sized rounds you want. And the trade-off essentially becomes FFTs, right? Like if you do 2 rounds of size square root n, then you have FFTs of size square root n. So I don't know, maybe the optimal round size isn't 2, maybe it's not like 1, or yeah, log n versus 1.
Yeah, maybe, I would next ask you about R1CS versus high degree gates. What do you think about those?
We are using high degree gates. I definitely support of high degree gates because it's more expressiveness, and I think, yeah, this is an easy question. I think it's definitely, because even for lookup table, you need some degree. But I think within like this high degree dimension, I think people are kind of like more leaning towards as low degree as possible within high degree, because every high degree will introduce way larger FFT and also require larger space requirement. So I think between R1CS and like this Plonkish, like this high degree gate, definitely like go into the Plonkish like expression. But then like within this, I think the best practice will be trying to use lower degree as lower as possible. And there are some way to how you kind of can do this. It's already part of the our ZKUM implementation, is that how you automatically lower the degree, because basically a degree 8 gate, you can decompose that into 2 gates and then multiply the result, and then, so basically trying to lower the degree, but having custom gate is definitely, I think, the future.
And finally, Yingtong, would you have thoughts on algebraic hashes versus standard hashes?
Where did I get that one? I think Mary might have more thoughts on that.
Sure, go for it.
I mean, ultimately, algebraic hash functions are faster, at least at the moment. I don't know if this will change, but they are faster to implement inside a circuit than SHA, to the point where I'm not even sure how feasible it would be to use SHA inside a recursive stack. Maybe it would be, but it would add quite significant overhead. At the same time, when it comes to actually evaluating the security of these algebraic hash functions, we kind of don't know how to do it. We don't know how to do it as in, they've been around for a few years now, but it's not as if everybody's using the same hash even, so it's not, even within Poseidon, people are using lots of different versions of Poseidon, so it's not clear how we can sort of develop trust over a period of time. I'm really not convinced that there's many, if any, people looking at it, and the reason that you would gain security in these things is by having lots of people look at it. So I think we need them, and I think as a community we need to think very, very seriously about what can we do in order to get more trust in these functions.
Yeah, I think one thing to add to this hash function topic is that people used to think, because when you're using Fry as your approver, and then because the verification is basically verifying multiple Merkle tree paths, which is verifying a lot of hashes, and then to do recursion efficiently, so they use hash function, use Poseidon hash function in their Fry, to commit to a large computation to reduce the verification overhead, because you are proving a bunch of Poseidon hashing verification circuits, so aggregation circuit can be smaller. But now I think the trend is changing a little bit, moving from this Poseidon hash to Blake 2F, SHA-256, or even more standardized hash function, because Poseidon hash function is relying on this kind of finite field operation, so it's still 10 times slower compared with this bitwise catch-check and Blake 2F and all those hash functions. And the first layer is proving become bottleneck. And then you just use some really good optimization, maybe look up maybe some other way to kind of reduce the overhead for hash in the aggregation layer, and then you get the best combination of both.
Oh, so you're saying so in that case you're optimizing for verifier performance?
So our planning for the first layer is poor performance, because if you use Poseidon hash, the Fry committing to a polynomial in Fry will take a long time, because Fry is computing that Merkle tree. So computing the hash become the bottleneck, then verifying hash using a circuit. So basically, using Poseidon hash, the first layer, the program layer will be very, very slow, and then but verification can be cheap. But if you change another hash, the first layer can be fast. The second layer verification circuit might be large. But if you can find some nice way to kind of reduce the SHA circuit, then you can do aggregation efficiently. I think this is already happening for most of the Stark circuit we are doing looking deep into. I think even for Plunky, as Plunky 2 or Starkey, they are looking to Blake 2F, I think, and RISC0 is using SHA-256 or something. That's my impression, because I think people are trying to kind of moving from Poseidon, or maybe there are some more efficient hash functions that both ZK friendly and also fast.
Right. Yeah, so final question. So this one, I guess, is a little bit more speculative. So I'm curious to hear from each of you what you think the sort of 5-year timeline for Snarks is in terms of first performance. So I think over the last 6 years, the performance has been about 1000x improvements every couple of years. at least what I have seen in like production practice. So I'm curious what your predictions would be for the improvement to hold up in the next 5 years. And then secondly, what application would you like to see snarks be used in the next 5 years? So maybe let me start with Mary, who has, I believe, been around longer than most of us here in this space.
I'm very hopeful for the next 5 years, at least in terms of performance. I mean, every time I sort of say, okay, we can't possibly get better now, we do. So I think I can't justify it, but I think we're going to get better. I think over the next 5 years, it's going to be another 1000x improvement, and applications are going to become more and more possible, just because that's been the general trend since I've been working on zero knowledge, which has been quite a bit of time now. In terms of the application that I really want to see being used very widely, I want to see verifiable computation being implemented and used. I want it to be the case that whenever you send any computation, this is probably not 5 years off, but let's say 10. Whenever you send any computation, it's not a matter of you trust that someone's done it correctly, but it's a matter of you send a proof, there's no way you could possibly have cheated, because that just makes it possible for actually a much more transparent world. Because at the moment we are having to hide private information, we're having to make it so that we're relying on trusted third parties because we can't do it any other way, and that can change.
Nice. Yeah.
Okay, so some alpha. I think scroll the KVM will become like 10 seconds, like in terms of proving time, like in a reasonable time frame. So that's my expectation. So eventually the KVM proof generation will become so fast, like 5 seconds or 10 seconds, so that within one block time you can get your proof, so that it can totally change like maybe how consensus work, how light client work, how PPS work, and a lot of things. So I think that's my expectation. So scroll the KVM prover, like 10 seconds, we'll see when we can reach there. I think I also expect to see like general verifiable computation happening. Like you are running a program, you are running a computer, but every program you run like just have a proof directly. Maybe it need to be embedded with some ASIC. Eventually, maybe Intel has some kind of ASIC like for zero knowledge proof inside their kind of like this kind of computer, and then like every time, every computation you are doing, you can get a proof directly. I think we are still far from there. I think what I expect practically say that firstly the KVM get really fast, and then some specialized structured circuit will be fast, like ZK machine learning, neural network, where you have this repeated structure, and then you find some way to customize and reduce the overhead, and then like general purpose thing like reduce the overhead so that people don't need to worry about the performance. That's I see as a practical way how we get there. Like firstly start with the most popular application, then like specialized structure circuit, and then like general.
I hope the performance trend continues. I mean, I think it probably will. 1000x in 5 years is a lot. I don't know. Interesting applications. One thing I've been thinking about a lot is specifically regarding like blockchains and payments, like client-side validated payments via recursive, folding or something like this. You attach a proof of validity to money, and then you don't have to post the proof on chain. You only have to send it to the recipient of the money. So I mean, there are people working on this, but this is something I've also been thinking a lot about, and seems pretty feasible.
Yeah, with regard to performance, Wei Dai had an interesting metric that he calls kappa. So it's like proving time over computation time. And yeah, like I don't think that will become 1. But yeah, I think I hope it becomes like, I think he said 3x or something eventually.
With what type of hardware for?
The other thing is the hardware. I think I saw that Ingonyama proposed something called the ZK score, which is modular multiplication ops per joule, something like that. So yeah, like if we're able, that's another metric that would be useful. Yeah, and very likely achievable with like very specialized hardware. And with regard to applications, Yeah, I think the two main applications are like basically anonymous credentials and verifiable computation. So for anonymous credentials, I'm a huge fan of like the ZK P2P project and like ZK email that allows us to transfer credentials across different trust systems. And for verifiable computation, I want to see it being used to hold public entities accountable. So for example, like when governments decide how to distribute their resources, like they might make a lot of private decisions, but we should at least be able to verify some desirable invariant about their methodology. And another example is like valuing carbon credits. I think it's also a very opaque process that we could improve, that we could audit using ZKML, for example.
Yeah, this is very inspiring. It's like a world in 5 years, like a world with ZK proofs just flowing around everywhere, it sounds like. Yeah, amazing. We're just out of time. So thank you so much, guys, for taking this time. And thank you all for listening.
Thank you, Nolan.
Thank you.